And we are back in business. All right, today we're going to talk about thermochemistry, which is the chemistry of heat and energy. And what we're going to do for this unit, we are going to combine this chapter and take off the last two sections and combine it with chapter 17, where we're going to talk about entropy and if a reaction will occur spontaneously or not. So today we're going to talk about this first section. We're going to have a quick review of energy, the two different types of energy, kinetic and potential, and then talk about how energy applies to different reactions. All right, so first off, energy is the capacity to do work or to produce heat. Okay, and one thing I want to point out is that heat is different than temperature. One single object can have a certain temperature, except heat has to be the transfer of energy from one object to another. Okay. So with energy, capacity to do work or to produce heat, it's the same application as it is for mass in any reaction. So energy in any reaction, it can never be created nor destroyed, but it can be converted from one form to another. So from kinetic to potential, or potential to kinetic. So that means the total energy of the universe is always constant. And it's known as the law of conservation of energy, or you'll see it as the first law of thermodynamics. Okay, so with these different forms of energy, the first one, potential energy, is energy due to position or composition. So you can think of that as an example, water behind a dam. Okay. It has energy, but when it's behind the dam, it's not currently moving, so that energy is potential energy. And then finally, once it's let through, it's converted to work when water flows through each of those turbines. So potential energy is energy due to position. That means the object is not moving, while kinetic energy is energy due to motion. The object must have some sort of movement. And if you've taken physics, the equation for kinetic energy, it's dependent on mass and velocity, and kinetic energy is 1/2 an object's mass times its velocity squared. Although we're not going to do any calculations for kinetic energy, you should know that it's dependent on mass and velocity. Okay, so if you look at this example, between the two objects A and B, ball A is higher than ball B. So that means, since it's higher due to its position, it has a higher potential energy than ball B. Okay, then ball A is let go. It knocks into ball B, and the ball B travels somewhat up the hill, although it's lower. So ball B is also lower than the original spot of spot A. So that means all the potential energy from ball A, some of it was converted to ball B, but the rest of it was converted to some frictional energy to the hill. As the ball's rolling down the hill, some of that kinetic energy gets converted to the hill. So actually what happens is the temperature of the hill slightly increases. Okay, so that means just because the position of ball B is slightly lower than ball A, that does not mean that energy was lost. It just means that some energy was converted to the hill as well, so overall energy is remaining constant. So energy is related to two things, both work and heat. So heat is the energy transfer between two different objects, whereas work, it's a force acting over a distance. So this is important, some distance. So that means in order for an object to do work, that means that it has to move. Okay, so work is dependent on an object. Heat, it's the transfer of energy between two objects. Okay. And now we're going to go over the difference between a state function and those that are dependent on pathway. So work and heat are not state functions, meaning they're dependent on path. Okay. However, energy is a state function. It doesn't depend on the system's past or future. It only depends on the present state. So what this means is it doesn't depend on how you arrived at the present state. So an example of this, if you're traveling, let's say from here, Cleveland, Ohio, to Denver, Colorado, and you want to find the change in elevation. So one of you could fly there, going over multiple states, or one of you could drive there, where you actually have to travel along all the different roads that lead from Cleveland to Denver. So even though you have had two different paths from here, from Cleveland to Denver, your overall change in elevation is the same. So the change in elevation from here to Denver is the same no matter what path you take. So that makes change in elevation a state function, just like it is for energy. Whereas something like distance, so the person flying, since they can fly directly from Cleveland to Denver, and the person who drives has to follow specifically the roads. There's no road leading directly from Cleveland to Denver, so that would not be a state function, since that's dependent on pathway. Okay, and when we're talking about energy, we're focusing on two different parts. The system, or the part of the universe, or in our case, the part of the reaction on which we want to focus our attention. So part of the universe, or the reaction in which we're focusing on. And then the surroundings is simply everything else. Okay, so normally the system is some sort of reaction container, and then the surroundings is everything else in that room and anything else besides the particular reactants and products. And for any reaction in which energy is released and energy is exiting the system, that means the change in energy is less than zero, meaning the change in energy is negative. So energy is exiting, that's exothermic, whereas if energy is entering the system, it's endothermic. That means the change in energy is now positive. Okay, so remember, endothermic, you should think about the word into. Heat is flowing into the system, and it's absorbing energy from the surroundings. And then exothermic, energy is flowing out or exiting the system. However, in every system and surroundings overall, the total energy gained and lost must be equal. Remember, the first law of thermodynamics, the law of conservation of mass, always applies. So now we have to think about a particular example. So here we want to know, is the freezing of water an endothermic or exothermic process? So think about, are we adding energy or removing energy. And you can think of this in terms of temperature. If we're freezing water, are we making it hotter or colder? So for freezing, we're cooling the water, meaning that energy is having to be released. So this is due to the fact you are removing energy in order to slow the molecules in water down. So if we talked about the opposite way, if we were asking for the melting of water, if that's an endothermic or exothermic process, that would be endothermic. Since we would be adding energy, energy would be absorbed because we would be making the molecules move faster in order to create that phase change from a solid to a liquid. Okay, so now looking at each of these examples, if your hand, when it's getting cold as you're touching the ice, that is an exothermic process because the heat is leaving your hand to the ice. But then if you think about now the system is the ice is getting warmer when you touch it, that is endothermic because the heat is flowing into the ice, if we're considering that the system. Then next one, water boils in a kettle being heated on a stove, so we're putting heat into that. The heat is flowing into the water, so that's endothermic. The next one, water vapor condenses on a cold pipe, so it's going from a gas to a liquid, so that means heat is leaving the system. It's leaving to condense the water from a gas to a liquid. And then finally, ice cream melting. It's going from a solid to a liquid, so heat is flowing into the ice cream in order to melt it. Now, we're going to skip these next couple slides and go to talking about internal energy. So with thermodynamics, it's the study of energy and its internal and its interconversions. And the internal energy of a particular object is the sum of its kinetic and potential energy. So all the particles in that particular system. And energy is dependent on two things. It's dependent on heat and work. And we're talking about internal energy, not overall energy, because the energy of the universe is always constant. So the internal energy of a system or an object is dependent on heat, which is Q, and W, which is work. And you have to be careful about both the magnitude of both heat and work, so the numerical value of each, as well as the sign. Is it positive or negative? Or what is the direction of the flow of both heat and work? So first off, for Q, for heat, the sign reflects the system's point of view. So that means for an endothermic process, when energy is flowing into the system, so that means Q, heat is being absorbed, Q is positive. So energy, and that makes sense, energy is increasing. Then the opposite, exothermic, So energy is flowing out of the system. So that means Q is negative. And that makes sense since energy is decreasing. Okay, so that is for heat. Now, once again, for work, the sign also reflects the system's point of view. But you have to be careful. If the system is doing work on the surroundings, if the system's doing work, that means energy is flowing out of the system. So that means if the system is doing work on the surroundings, work is negative. And then the opposite, if the surroundings are doing work on the system, energy flows from the surroundings to the system, meaning work is positive. The change in energy for a system in which 13.6 kilojoules flows into the system and 1.4 kilojoules of work is done on the system. So we use our equation for delta E for internal energy, Q plus W, but we have to think about what are the signs of both heat Q and work W. So first off, it says 13.6 kilojoules of heat flows into the system. So that means that it's an endothermic reaction, which means the sign is positive. And then for work is being done on the system, making that work positive. So we add these two together. So it's adding them together, 15 kilojoules. Okay, so you have to be careful with work and determining its sign, because for an expanding gas, the change in volume is positive, and that means delta V and W and work will have opposite signs. So work is pressure times change in volume. So that means if the volume change is increasing, that means the work is negative. Okay. So that means when gas is compressed, delta V is negative, which makes work positive. And when gas expands, work flows into the surroundings, making work negative. Okay, so now looking at delta E, so an endothermic process that performs work. So that means that it's endothermic, that means Q is positive. And then if the system is performing work, that means that the work is negative. So if we're thinking about the sign of delta E, if the magnitude of work is greater than heat, that means delta E is going to be negative. But if the magnitude of heat is more than it is for work, that means the delta E will be positive. Then if we think about the opposite, if the process is exothermic, so Q is negative, and work is done on a gas, so that means work is positive, the opposite is true. So if the magnitude of work is greater than it is for heat, then delta E is positive. And then if the magnitude of heat is greater than it is for work, that makes it negative. Okay, so energy is dependent on both heat and work, and it's dependent upon the fact if heat is flowing into or out of the system, and if work is being done on the system by the surroundings, or by the system to the surroundings. Alright, that's all for this time. See you next time.